Hi, I'm Atul and I am in London right now.
Hi, I'm Paul and I'm in Burnley, Lancashire right now. Okay, so today we're going to look at equilibrium constant problem KP, where we're going to use a bit of algebra. So you'll see as we go into it. So as ever with equilibrium constants, we're going to use the ICE method. So what we've got initially, what we've got changing, and what we've got left at equilibrium. So we know initially we've got 0.5 moles of A, 0.5 moles of B, and then unusually we haven't been informed what's changed or what we've got left at equilibrium. And it's worth putting in there we've got nothing of C at the start. So what we're going to have to use here is that we're going to have to use algebra. We're going to have to say that X moles of, let's say, C has been formed. Or perhaps better to say, because it's 2C, 2X of C has been formed. And therefore the change in C must have been 2X. And what would the changes in A and B be?
So that's, well, half of 2x, which would be x.
Excellent. So what's left of A would be our initial take away our change. So that would be a half take X. And the same for B, a half take X. And then, because this is Kp, what we do next is the mole fraction, which is the number of moles divided by the total number of moles at equilibrium. So there, what would our total number of moles at equilibrium be if we added that row of equilibrium moles up?
Yeah, so that's all of it just added up to this plus that.
That's it.
I can do that just roughly in my head. Minus x plus 2x will be no more x's. 0.5 plus 0.5 kicks you to 1.
Excellent. So we can write down our total number of moles at equilibrium is 1. And therefore our mole fraction for A would be a half take X over 1, which is as a half take X. Same for B. And for C, 2x over 1, which is just 2x. And therefore our partial pressure of A, B and C's mole fraction times total pressure. And it hasn't given us total pressure, but it's just called it P. So our mole fraction, our partial pressure for A is mole fraction times the total pressure P. Exactly the same for B and for C. So now we know our partial pressures. So now we can put those into our equation for Kp. So Kp is products over reactants raised to their powers, or partial pressures of products over reactants raised to their powers. So for, we can write it out So it's the partial pressure of C squared over the partial pressure of A times the partial pressure of B. So that would be 2x all squared, or 2x times P all squared. What do you say?
Yeah, you can just edit that out, can't you? Yeah.
And on the bottom we've got half minus x times P all squared. So what do you notice about that equation?
Well, they both have a square, and yeah, my first guess is there's a p square eventually here in the p square and the denominator, so there's a p square in the numerator and denominator, which would cancel them out due to equivalent fractions.
That's exactly it. That's why they haven't given us a total pressure, because the pressure's p squared on top cancels with the p squared on the bottom.
And then on the top you'll end up with 4x square, and you'll end up with a quadratic on the bottom, surely. It says, so that's 4x. I can have a go at it, so I'll just 4x square 0.25 minus x plus x square. Or I can say
Before we don't, if you notice it says we don't need to use a quadratic equation.
yeah.
So what's another way of doing this? That is possible, but it's a long-winded way.
Yeah.
Yeah? So at this stage, Kp is equal to 2.55.
Of course. Okay. Yeah.
So is there anything we can do here without expanding the brackets?
Yeah, of course. Yeah, no, I didn't pay attention to that one. Went for the heavy-handed maths approach. Yeah, probably the easier way is just to square root both sides. So you would square root all of this, and then you square root that as well.
Okay, so could you do that?
Yeah, let's. If I do square root of 2.55, 1.597 for now. 97, which we can round later on, equals 2x over 0.5 minus x.
And now do you think somehow you could work out x?
Yeah, so that's really a linear equation rather than a quadratic equation as such. So I'll proceed and solve that. So multiply both sides by 0.5 minus x. So that takes me to 0. Minus 1.597 x equals 2x, which I can proceed to solve as a linear equation. Add that. So 1.597 plus 2, 3.597x equals 0.7984, giving x equals 0.22. Yeah, that's 222, surrounding 2. We got two significant figures, I think, so let's just call that 0.22.
Excellent. So now we know x. Can we calculate the number of moles of each species at equilibrium?
Yeah. So at equilibrium, it's simply given by these expressions. So I'll just write that out here again. At equilibrium, this one is 0.5 minus 0.22. In fact, I'll just explicitly write that out. This one is also 0.5 minus 0.22. That's just 2 times 0.22. 0.28, 0.28, that's 0.44, and that's A, B, and C, just to be clear again.
Excellent. And that's the number of moles of A, B, and C at equilibrium.
Brilliant. So that's the final answer.
That is the final answer.
Great. That's a very useful way to do it. Yeah. Look forward to the next set of calculations and problems.
Okay. Thank you.
Great. Thanks. Bye.